one, for example, to promote one layer, protective layer, we can cut mechanically, we can transfer this for a substrate. It's our substrate when we are talking about the transference here, and we have the electric contact. Look for that we have the electric current here and the electrochemistry here, okay? The electric contact for heterojunction is here, and if you are talking about of the electrochemical conductivity, we are talking about of the orthonormal to the plane of the electrode. So this is a picture that we can see here. More here we have our layer transferred on the contact, and after we use a nitrocellulose resin in order to isolate our systems. Okay. This is one image of in situ FTR microscopy. This technique can, for example, we can have more than 4,000 spectrum on range of one delimited area. So we can see here that we have a nice isolation, and we have here the peaks associated of the nitrocellulose. The resin, nitrocellulose resin, and we have the isolation and the good isolation from the graphene one. Sorry. This is where you see more details about that. This is after transfer the graphene. Generally, we have this kind. Okay, in the literature, we see nice pictures, but if we come back to the real world, we see a lot of defects on the graphene, okay? We can have folding, we can have the ripes, and we need to consider this kind of system. I will show some two works from our group. One talking about removing metal even after etching, chemical etching procedure. Okay, and one experiment that we have the idea to create one battery on chip by using this monolayer. These results, Rodrigo are presenting here, okay? Here we have the cyclic voltammetry. Cyclic voltammetry, it's an electrochemical technique that we use to observe electrochemical process, applying one current or applying one voltage, or on potential. In this case, we call it the overpotential. And even though we have the etching, the chemical etching, CVD graphene, okay, we have a contamination, okay? So before this work, we have observed in the literature several works that has measured copper on the surface than the properties of real graphene, okay? We prove this by using other techniques, and also if you make one electrochemistry change the pH, we see the shift on the peaks that is related to the potential of the oxidation of copper on the surface. This is fit very well with the plots of pH then potential, okay? And we reproduce two works from literature. I will not show this work here, but we reproduce two important works in the literature. The first one by using, for example, the electrochemical reduction of a Coumadin hydroperoxide and L-glutathione one, okay? If you use the graphene produced after chemical etching, we have this result here. We have a very nice electrocatalysis for reduction of this peroxide. So, and also if you use the same electrode, we have the very nice oxidation. Now, if we use the e-etching or the electrochemical etching to clean the surface, we observe the exactly profile that we have the graphene. So we are talking about that the catalytic property that comes from the graphene is not come from the graphene, okay? It's coming from the parasitic impurities, okay? With this idea, we had a very nice approach to promote the electrodeposition of some metals. And if you remember, we use 2 layers of graphene to produce 2 electrodes in order to create a Daniel pile or Daniel battery. Do you remember on the collegial, on the high school, the Daniel pile or Daniel battery is a copper zinc battery? Okay, very, very, very old one. Okay, why we do this? Because when you see here in this workshop, sometimes we need some power to make the microfluidics happen and something like that. And we thinking about, okay, in order to have one autonomous microchip, it's important if, for example, we have one source of power, and we promote this by using 2 layers of graphene. This is the result of our work. When we have here 1 layer of graphene with a zinc, it's 1 layer of copper, and we have 1 battery of zinc copper. Interesting that it's after electrodeposition, we have different profile. I am not talking about the morphology or something like that. It's a different, it's under investigating in our group. And here we have, for example, the monolayers before and after electrodeposition with a copper and zinc. We have the oxidation of copper, of a zinc, and if you have, for example, copper ions on the electrolyte, we can produce 1 DDP between these 2 electrodes. We can produce electricity. So this is our other view of the electrodeposition. It's optical microscopy for both copper and zinc. Okay, this is the final configuration of our device. When you have graphene zinc, graphene copper, and you have 1 chamber that it's composed by electrolyte, and you put 2 gels here, 2 kind of interfaces here. We have a 3 interface in order to, because if you have just electrolyte, the battery, we can consume fastly the current. So we can avoid, or we can cause some delay in discharge of this battery. We use a gel approach. In this case, we use it agar, and here we use a 3-dimensional chamber that it's by using, for example, polylactic acid in 3D printed cells. So it's a very simple configuration, and we have the motion of the ions here, and we can use it here, for example, for 1.1 volts. Okay. Interesting that we can use more than 8 hours. This is a OCP or OCV, open circuit voltage. We use a very small value of resistance, and we can promote here the consumption of a current for more than 8 hours. So this is our chip. That it's interesting that the chip can supply a macro system. So I think that for micro system, it's also this is on video. I don't know if it will work here. I will try. Okay. In this video, we have our microchip here connected with this calculator, and we put the electrolyte. Okay. When you put the electrolyte, it starts to have immediately current. So it's a fast system for delivery energy power. So, and after we use it for several things, how long we can use, how much energy we can provide with the system. And now I would like to talk about a fundamental question. It is the work of Luciano. Luciano has made the same system, removed the copper parasitic one, but the configuration was different. They use a functionalization of the surface with benzoic diazonic salts, and by using infrared microscopy, they observed, for example, where is the functionalization of the graphene. This is, for example, optical microscopy of a crystal of a benzoic acid diazonic salt. We can localize this, the extraction of a CO, and also we can use this map to identify the localization of functionalization in our system. This is another kind of graph of plot that we have of a hot points in our sample, and he does the electrochemical reduction for functionalization applied on a potential electrode, and he tried to make the mechanism of this using, and he has observed that we don't have a homogeneous system during the functionalization. This is important results because the last results from a Strano group from MIT show a very, very broad peak for identification functionalization. This is the first results that we have a very nice infrared signal of a monolayer of diazonic salts. They do some investigation about that. Okay, if there are no homogeneous system by diazonic salt and with metallization is the same. So they observed by very controlled system that sometimes we have some places top of the graphene that we don't have the metallization. So if you don't have the metallization, something happens on the distribution of potential on the surface. They looking for example, for low and high load of materials on the surface, and he observed that for low density on the surface, the metal prefers to be close to the electric contact. However, if you have a high current path through the graphene, we have the delocalization. It's coordinated with a very, very nice paper that talking about anisotropic behavior of mesolet direct fermions in graphene with a periodic potential. So it's the first experimental evidence that the charge distribution on graphene is anisotropic. We are studying more this system in order to figure out these problems. Okay, thank you very much for your attention, and also I would like to thank the financial support of our group from FAPESP and everyone that is working in this project. Many Professor Cannon that is our collaborator. This is a very nice environment for collaborator. We really like to find some problems in the literature in order to figure out. This is one T in his house, and this is our group in São Carlos. Is a old picture is some students are professor in Piauí, Goiás, and the other kinds of parts in Brazil. And these are more recently pictures, but I am not in this picture. I don't know, but I am not there. So, and thank you very much for your attention.
Questions?
Thank you, Professor Frank. Very nice talk.
Thank you.
In your opinion, what's the main challenge to make graphene on chip nowadays?
So, firstly, use large area large area. When I talk about large area, I may not talk about putting several kinds of layers atop, or control this. The size is not problem, but control the quality of a large size is problem. This is a main challenge also. The second one is understand the graphene. We don't understand the graphene. Because sometimes we can have a really nice papers and a really nice works showing that okay, graphene is unusual. If you search in the literature unusual in the graphene, this is only an easy one. You know, so sometimes I think that good experimentation with graphene is important. People with the advent of productivism, produce papers, we are losing one idea to make slow science. Slow science in graphene is important. For example, these results, for 5 years ago, we started this research. You know, so slowly to understand and see if it's happen again, reproducibility and some stuff. This is important in graphene. This is the second one. And the third one, it's a challenger for chemists. Synthesize using other chemical routes to produce graphene, because chemical route, definitively, in my opinion, is bad. We need to think about other idea. Exfoliation is not so good. Hammer's methodology is not so good. We don't have a pure monolayer without defects or something like that. CVD is the best one, in my opinion, also, but other methodology is quite necessary in this direction.
Thank you. I have just another question. I have seen many high-quality graphene grown by CVD in the literature. When I look to your CVD, it seems that you have a lot of defects. What do you attribute such amount of defects in your CVD?
Because we use real samples. We used the best graphenes for the best groups in the world. We test that. We use a CVD produced in Max Planck, produced from Manchester, or something like that. One thing is that if you choose the best one to show for everyone. Other thing is if you choose the real sample that they are in graphene. Graphene has holes a lot, not holes defects in the atoms structures. Holes that I talk about are big holes in the large areas. Okay, sometimes it's possible to obtain one sample with this characteristic. So, but every time it's not possible until now. In my point of view, I don't know if there is some example in the literature by using electrochemistry. I cannot see that. Okay, but I think that in the near future we can have good samples for that.
Have you tried to map the quality of your graphene samples by Raman?
Yes, it's talking. Sorry, fracasso. Yes, the same results that everyone has. Two peaks, and we calculate the effect the same. In those papers, we have the same characteristics. Hello?
Very nice talk, Professor Franke. I would like to do a question you about the applications of graphene electrochemistry. So graphene depends of your application. You choose the type of graphene that you work. For example, CVD is very good for sensors in capacitance, application FT devices, RF devices, and others. And you're thinking about electrochemistry, sometimes people are using more reduced graphene oxide by Raman's route, because sometimes defects is good for electrochemistry, and the activity is more in edges than basal plane. And the question is, why you are using more CVD graphene for this electrochemical application instead the RGO? That is it.
Yes, I agree. You are right. However, it's interesting if you are talking about, for example, some electrochemistry like a biosensor. Let's put one application, biosensor. Why we don't have on the market one electrochemical biosensor? We have the glucosimeter, for example. It's why? Because we need a print thing of our molecule. If we're talking about electrochemistry for sensors or molecular recognition, we need to know our surface. Okay. In this case, the monolayer, it's interesting for this application. For electrical applications such as field effect emission, field effect effects, it's not, you do not see the fingerprint of the molecule, we see the fingerprint of our substrate. If you think about that, we need to see what is the best composition of our system, and to see that. Because, for example, one molecule that has a potential has an energy, and the energy is unique for this molecule. Because of this glucosimetry, by using glucose oxidase, works. Just this works. Even though, however, if you know the composition of your sample, okay, this signal is coming from this guy, okay? For graphene, I think that the change on the surface occurs every time when you are talking about electrochemistry. One time if you can have reproducibility, but it's dynamic system because we don't understand, for example, the appearance of new holes after experiments. So it's more complicated, in my opinion, for that. But you are right. Depends on the application. Graphene oxides or some other kinds of these materials is best.
Well, this is a very exciting field of research, but unfortunately we have to run with the program. But Frank will be here today and tomorrow, and there's a lot of posters, and you can discuss more under this poster section. So let's thank again Frank. Sorry. Blame Murilo. Our next speaker is Wendel Carlos Tomazelli Coutro from University Federal of Goiás. And I almost don't have to read the biography of Wendel because I know Wendel for a long time now. He got his PhD at the University of São Paulo, at São Carlos also, with Professor Emmanuel Carrilho. And after that, during this PhD, he got a kind of stage at the University of Kansas with Professor Susan Lund. And right after that, so when he finished, he got a professor position there at the Federal of Goiás. So Wendel is a very impressive researcher. In a short period, he got many theses and dissertations concluded, and more than a dozen now, I think so. Yeah. And about more than 60 papers published right now. I think more than that, isn't it? And is a very active researcher also, so you can see on the watching his presentation. So, Wendel, thank you very much for coming again for this workshop. He was planning to present yesterday, but he was in a kind of negotiating a building in the university, so this is very nice to hear that everything is running very well in your career. Thank you, Wendel, very much.
Okay. Good morning, everyone. Thank you, Fracassi, for the presentation and also for the invitation to give a talk here. It's my pleasure, firstly, to meet Professor Vandenberg. He's one of the most widely researchers around the world. And in our case, I tried to select a few reports from our group, in special selecting the paper platform. We have so many staff using this platform for different kind of applications, and I will try to show you a few examples in 30 minutes, I hope. Well, 30 minutes, yeah, okay. Well, firstly, I'd like to show you other areas in our group. We have so many staffs in electrophoresis microchips, also in some simple and cheap microfabrication technologies for PDMS and glass, or using even toner, and also paper, of course. In the last 2 years, we are using a 3D printer to make it very easily microfluidic device. And also, I will show you some examples using paper microfluidics. About CE microchips, it's very nice because we have solved some common problems in this area. Here is very fresh thesis. We have submitted this paper to analytical chemistry last week, and we are using the electronic micropipette just to promote the hydrodynamic injection. It's very impressive because we solved the discrimination. We solved the problem related to the discrimination of the sample. It's very impressive. You can see here the difference of the peaks is very close. Here is completely different. Another reports, we have 2 posters, I think, here. The first one is the use of CE chips for studying the authenticity of whiskey samples. Is very nice because you can analyze the sample and also drink. Some fake samples, very impressive. Here is a separation of sugars. The poster of Hierárquica.